Our lecture for today is an experiment on the flow of water through a capillary tube as an introduction to decay curves and the study of half-life. History of radioactivity. The history of radioactivity really began with the discovery of X-rays by Wilhelm Röntgen in November 1895. In 1896, Henry Becquerel found that uranium salts could activate a photographic plate in the absence of light. Also, they could activate air so as to discharge an electroscope. He suggested the term radioactivity by referring to the phenomenon of radiation activity. In 1902, Marie Curie succeeded in isolating 0.1 gram of radium. Pierre Curie exposed his arm to the radiation from the radium and studied the healing of the resulting burn. In 1934, Frederick Joliot and Irene Curie produced radioactive phosphorus by bombarding aluminum with alpha particles, and thus produced the first isotope which does not occur in nature. Radioactivity. Radioactivity is a number of disintegration per second. Its unit for measurement is Becquerel BQ. There are two main sources of radiation found in the environment. 1. Natural radioactivity sources, which include terrestrial, cosmic rays, and cosmogenic. 2. Man-made radioactivity sources, which include medical, fallout, and nuclear power. Ionizing radiation. Ionizing radiation consists principally of electromagnetic waves like light, for example gamma, and X-rays or charged particles, for example alpha and beta particles, and of neutrons. As shown in this photo, radiation exposure. Exposure is an act or condition of being subjected to irradiation. The types of exposure are: external exposure, irradiation by sources outside the body; internal exposure, irradiation by sources inside the body by inhalation or ingestion, or through the skin. The actions of ionizing radiation. The actions of ionizing radiation on cells are two types: direct action, indirect action. Both actions are involved when a charged particle passes through a cell. Both actions can cause damage to the cell, but by different mechanisms. 1. Direct action. Direct action occurred within milliseconds following irradiation. This type of action causes a number of physical and chemical events are used to describe the death of the cell. 2. Indirect action. Indirect action occurs when a molecule reacts with a molecule or the product of a molecule that undergoes direct action. Since the human body is an aqueous solution containing approximately 80% water molecules, when ionizing radiation interacts with water molecules, they dissociate into other molecular products, and this action termed the radiolysis of water. Radiation injuries from ionizing radiation. Radiation injuries can be divided into two classes: somatic effects, in which the damage appear in the irradiated person himself, loss of hair, reddening of the skin, etc. Genetic hereditary effects, which arise only in the offspring of the irradiated person as a result of radiation damage to germ cells in the reproductive organs, the gonads. The radioactive decay. The basic equation describing radioactive decay is A is equal to a naught e to the power of minus lambda t, where A is the activity in disintegration per second. A naught is the initial activity. Lambda is the decay constant. T is the time. We can express the previous equation as A is equal to lambda n. N is the number of radioactive atoms. Half-life. Some nuclei are unstable and decay. Others are stable and last forever. The most unstable nuclei decay the most rapidly. That is, they have the shortest lifetime. Two factors determine the length of time the radionuclide is in the organ, or the effective half-life T half f. The physical half-life T half phi is the time that needed for 1/2 of the nucleus to decay. The biological half-life T half bio is the time needed for 1/2 of the original atoms present in an organ to be removed from the organ, and it is independent of whether the element is radioactive. T half effect is equal to the result of multiplying T half bio by T half phi divided by the result of summation T half bio and T half phi. The decay constant is related to the half-life by simple equation. T half is equal to log T divided by lambda. The medical applications of radiation. 1. Ionizing radiation is used to diagnose numerous medical conditions. The doses in our EMS from diagnostic procedures are usually small. 2. Large doses of ionizing radiation are applied for therapeutic purpose, almost exclusively for the treatment of cancer. The risk of exposure versus the benefit of the medical procedure is usually carefully considered. As in any medical procedure,